Welcome to the last problem of our friction worksheet. I'll read it aloud for you. I am going around town when I find an old rust bucket of a muscle car. Be still, my beating heart. It has locked up wheels. It has a mass of 450 kilograms. Basically, the entire inside of it has been gutted out. I know I can only push with a force of 956 newtons. I devise a counterweight system that will pull up on the car with a certain mass attached to a rope. What mass would I need to add to the counterweight for me to be able to move the car? P.S. The coefficient of static friction of rubber on concrete is 1.0, so it is equal to the weight of the car. So, I don't have any kinematics in this problem, so I'm going to start by drawing a free body diagram and figuring out the forces involved. So, free body diagram, it's going to be a point. This car has a force of gravity bringing it down. It has a force normal, and in addition, I am adding a force of tension pulling up on the car. So force normal plus force tension. That's going to be all of our forces upwards. And then it has a force of friction that's going to keep it rooted in place. And I'm trying to equal that with my applied force that I'm calling F1. So let's take a variable list based on this free body diagram. So first we have an F net. Then we have a force 1, which is my applied force, a force of friction, a force of gravity, a force normal, and a force of tension. Then, now remember, what we're doing here is an Atwood machine. We have the car, M1, attached to the Atwood machine, which has a mass, M2, on the other side, pulling up the car, reducing the force normal, thereby reducing the force of friction. So I have two masses in this problem. And what I'm looking for is mass number 2. That's what I want to know. And then lastly, I have a mu s for the coefficient of static friction. So let's go ahead and grab our values from this problem, see what we already know. So the rust bucket of a muscle car has a mass of 450 kilograms. The mu s is 1.0, so that's going to be incredibly unhelpful. Let's see. I can push with a force of 956 newtons, so that's our F1, 956 newtons. And is there anything else that I can determine from this problem? Not really. I know that I have a certain gravitational acceleration, equal to negative 9.8, and I know that this car will start to move when my force that I'm applying is anything above the force of friction, even the smallest amount of newtons above the force of friction. So really, I'm looking for F net equal to 0. More precisely, 0.00000 infinity 1. So just literally anything above the force of friction static. Because once I've started moving it, that coefficient of friction changes to kinetic, and that's less. So once I start moving it, I'll be able to keep moving it. So I just need to get this force of friction low enough that it's just under 956, even if it's just the smallest amount under 956, okay? So effectively, F net is gonna equal 0, all right? So F net in this case is our equilibrium of forces. Remember, that was this confusing symbol called sigma. So sigma F is equal to F1 plus the force of friction. So these two should equal 0. That's what we're looking for here. So first off, let's calculate the force of friction, the current force of friction. Let's just go ahead and figure out what that is right now. That'll help us get a better idea of what's really going on here. So the current force of friction is equal to, remember, I've got no other forces currently working in the Y. I'm going to be adding a force of tension, and that will change things, but for now, I don't. So my initial, we'll write that, initial force of friction is going to be just mg mu s. Should really get better at writing mu. It'll come with time. So, mass is 450 times gravity, negative 9.8, times a 1.0. So my force of friction right now is negative 4,410 newtons. That's a lot. Okay, so what's that difference? Currently, that difference between the force of friction and my applied force is negative 3,454 newtons. And that is a static, not gonna do anything force. I need to find a way to get that force removed by way of this mass. So how do I do that? Well, I need to set this equation to be true. So I say F net is equal to 0, so I need to say 0 equals F1 plus force of friction. And since I know that force of friction is actually equal to the force net times mu s, then I'm going to play with the force net. Now the force net is the force that the ground is pushing back up on the car. So if I lighten the amount of gravity that's pushing down on the ground, then that force net is going to go down. So I need this Ft, this force of tension, to be in addition to the force normal. So that's going to look like this. Force of gravity is equal to force normal plus force of tension. If you remember back to our first problem in the balanced versus unbalanced forces, I tried to pull up on a car by lifting up on the bumper, and I did this same thing. And then me and my friends got in the car, and we added the force of our mass to the force of gravity of the car, and that was the new force normal. So my force of gravity is not going to change. It's still going to be that same mass times gravitational acceleration, okay? So what I'm really saying here is, since I have a mu s of 1, I need my force of friction and force normal to ultimately equal this F1, the applied force. Okay, so that takes a little bit of backwards thinking. I understand if you don't get this one. This is a little more difficult. So my F net, I have a value specifically that it needs to be. So I'm going to set it to that value, and I'm going to use that to figure out the force of tension. Okay? I already know the force of gravity because that's just mg. It should equal Fn plus Ft. Okay? Now, based on the way an Atwood machine works, this Ft, this force of tension, is actually going to be the force of gravity of this mass pulling down on the other side of the rope. Okay? Remember, a pulley just changes the direction of the force. So this is still going to have a force going this way, and the pulley is going to cause it to be a force pulling up on the other mass. Okay? It's still going to be the same force of gravity. So what we're really going to have is m1 times the force of gravity is going to be equal to Fn, which we have a specific value that it's supposed to be equal to of the F1, plus m2 times that same g. Okay, now those are actually pretty manageable numbers. That's an equation that we can solve. Because we have m1, we have g, we have what Fn is supposed to be, and we have m2. So this is a very solvable equation. It just took a few extra steps for us to set it up. That's really the direction that we're going to be going in physics, okay? We started out with a fairly complex equation. The S equation is a more complex equation. It's a quadratic equation. It is mathematically tougher to deal with. But now we have these. Something plus something equals something else. That's a simple equation. If we just break that part down, is that simple? 2 plus 2 equals 4. That is simple. It's the variables that get confusing. Okay? We're not going to get much more complex than this. We're going to get into energies, and pretty much everything is still going to be a single term equation. So So remember that as we move on. Plugging in our numbers, we're going to have this negative m1g equals fn plus m2g, and we're going to do something different with this in just a sec. So negative m1 is 450 times a negative 9.8 equal to fn, which should be 956, plus m2 times a negative 9.8. Now before we go any further, let's talk about this negative 9.8. Should it be negative? Because in our case, we're thinking in terms of this m1. This is our reference. And this pulley is changing directions. So while at m2, 9.8 is negative, at m1, that 9.8 is positive. It's pulling upwards. So that can be a little confusing when we are working with pulleys. So we have to keep in mind that they change direction. So while this over here is a negative total thing times a negative, resulting in both of those being positive, this over here ends up being negative for our current frame of reference. That might be confusing, but just trust me, this force of tension should ultimately be a positive number because it's pulling up. So we need to adjust our gravitational acceleration to coincide with that force of tension, okay? So 450 times 9.8 is going to give me 4410 equals 956, come on, plus m2 times 9.8. Okay, so then, first thing I need to do is, if I try to divide by 9.8, I've got to divide both of these by 9.8. So the easiest thing to do is going to be subtract 956 from both sides. Okay, 4410 minus 956. It's going to give me a result of 3454 equals 9.8 m2. So then divide both sides by that 9.8. 3454 divided by 9.8. It's going to give me 352 equals m2. Now does that make sense? Okay, 352 kilograms, that's less than 450. That should make sense. It should be less than 450. If I had something more than 450, then what I'd end up having is this M2 would be heavier than M1 and it would cause it to pull off of the ground. So it's got to be something less than 450. So that's an easy way that we can check this math. Okay? So M2, 352 kilograms. Okay? Great. Now, at this point, we should have a positive number because mass is a scalar quantity. It's not a vector. It's never going to be a negative number. You can't have negative mass. That wouldn't make sense. So, if we ended up with a negative mass, that would tell us that we have flipped a sign somewhere or that we got confused on a sign somewhere, which in a problem like this is really easy to do. We have to remember that that pulley is there. It is changing the direction of a force, specifically this force of tension. Okay? Force of tension in this problem is equal to the opposite of the force of gravity on M2. Okay? Does that make sense? No? Great. We'll talk about it. All right. Thanks, guys.